topic that I'm explaining today is very similar to what we have already had in the past few weeks. We are going to discuss adversarial search and game playing. And so what we're going to explain today, focusing this week, is that so far in search problems we were starting from an initial state, right? And what was the goal? What was our objective? In all the searches that we have covered so far, informed, uninformed, we had one common objective. And what was that? Finding the goal, right? And so here is one of the main differences of what we are covering this week. So in adversarial search, it's not only about reaching to the goal state, because we have another player who is actively trying his or her best so that we cannot move, we cannot win. So when there is another player adding to the game, so everything is changing, right? So there is it's not more like there is one specific path that is the best way, for example, to reach the goal, or for example, we can find an optimal path. No, that's not the case anymore, because we have another player, and is trying to avoid us at each step and minimizing our chance of winning. So let's first talk about the different types of environment that we deal with in AI. So we've talked in the first few sessions, if you remember, when we were talking about the AI agents and environments, we're talking about different types of environments. And one of them was multi-agent environment, right? When there are more than one player or more than one agent acting in the environment. And then we also have cooperative and competitive environment. And what does that mean? So when we talk about cooperative environment, it means that the agents that we have, so it's a multi-agent environment, right? So we have multiple agents, multiple players. So they all work toward a common goal. Whereas when we talk about a competitive environment, which is the focus of this course this week, is when the agents have conflicting goals. So can you give me an example? Example plays or games that there are multiple agents involved, and then it's competitive, right?
Chess.
Yep, chess is one. What else?
Checkers.
Yep, checkers. So Tic Tac. So there are lots of examples of the multi-agent environments where we are having competitive agents that trying to minimize their chance of winning, right? Maximize their own chance, but minimizing their opponent's chance. And so here is actually where we come to adversarial search. And examples, as your friend said, is, for example, chess, poker, and so on, that there are we have more than one agent, and imagine, let's say you have two players. One player who is, for example, we call it Max, is trying to maximize his chance of winning, and at the same time, the other player is trying to minimize his chance, okay? So that also is showing another difference with a game theory. So what we define, for example, when we define games in AI versus games that we, for example, have in game theory, so it's a small difference, mainly they're the same. But in game theory, which is a branch of economics, the focus is not on the competitive environment that we have agents acting so that one of them wins. They could be competitive environment or cooperative environment. The main focus is on the strategies, on the decision-making strategies, to see, for example, how, for example, the agents can influence each other. And so here are just types of games. again, if you remember, we had perfect different types of information, right? Sometimes we have perfect information or imperfect. What do you remember? What was the difference? What does perfect information means?
Like, it's that you know everything about your state as well as the enemy state. Everything is visible.
Yeah, so the players know, for example, what is the result of their move, right? So, for example, if they make this move, this happens, or so on. And there is like one way for like at least each player to figure out how to move. But in imperfect, when you have like imperfect information, is that when your players do not have any knowledge of the environment, right, or the previous moves. And they may, for example, play simultaneously. And so how about chess? So chess, as you see, is, for example, perfect information, right? Because, for example, agent A plays, then agent B plays based on the moves that agent B made, right? So your action defined the other player's next actions, right? And checkers and some other examples. And we have also two other factors, which are deterministic or if you like have it by chance. Anyone remembers what do we mean by deterministic? Anyone from this area of the class? No? No one? Yeah?
There is, you can determine what the best move might be or what the best state.
What would be the best state? Yeah?
It says that when you take an action, your next state is either deterministic, meaning that you just, when you take this action, this is only going to happen. But if it's by chance, then if you take this action, you may end up.
Yeah. So, and you see the examples. For example, if you have played Monopoly or Backgammon or, like, for example, poker, you see that, for example, these are the games that have the factor of chance in them, right? So you can't, like, determine all the outcomes. And so just more discussion on games versus search problems. So, for example, when we were talking about different search methods, like, for example, BFS, A*, DFS, and so on, we assume that our world, and by world I mean the environment that we are playing, right? So we assume that it's fixed, and we like had an initial state, and then we had a goal state, and we use different techniques to reach from the initial state to the goal state. And so the solution is heuristic method for finding goal, and heuristics and CSP techniques can find optimal solution. And we already covered constraint satisfaction problems. We talked about heuristics and how they can help us to reach to the goal state, right? So what was your evaluation function in search? So it was the estimation of the cost from, can I help you?
I'm a student.
Okay. And so estimation of the cost from start to goal, right? And you had, for example, if you remember when we were talking, for example, heuristics, which was the estimation of the cost, for example, from where you are to the goal. And we also had another function to evaluate, for example, where we had the exact actually cost from the initial state to the state that where we are. And so that was all about the search, right? For instance, for path planning, scheduling activities, when we wanted to schedule, for example, courses, when we wanted to color the maps, and so on. Now in games, the solution is a strategy. So we have time limits, we have another player who is our opponent, and we have to think about like his moves too, and his actions also affect our actions. So that opponent, like introducing the other agent who is actively trying to block us, is actually changing everything here. And the examples are like chess, checkers, and like the other games that you already mentioned. And so the main takeaway so far is that in like adversarial search or games, our goal is not only reaching to like a fixed goal state or like finding an optimal path, but we want to also win, right? We want the other opponent lose, and so that's another factor. So there are some formal elements of games. So I apologize for the boring slides so far. So I try to also include some examples here. But first we have to know the terminologies and everything, right? So we have to know what I mean, for example, by the actions, result, terminal state. So we start from initial state S, and then we have set of players. So here we mostly focus on two players games, okay? So define who is the player in a state S, and then we have set of actions, which are the possible moves that we can make from each state. For example, if you are playing, for example, Tic Tac, then, for instance, if X is positioned at specific states, right? So if you have like something like this, so this is the Tic Tac game, right? So you have, for example, X, X, O, X, right? And then if this is the current state, what are the possible moves for O next? O could be here, right? So this is one state. O could be here, right? So these are the possible moves for the next player. So these are X and O will be our players here. And then we have set of possible moves from the state where we are. And then we have a result S and A, which shows the state after action A is taken on state S. I was so awful. And then, so you, for instance, this is what I just mentioned, right? If you take an action A, what would be the result after you took this action? And terminal S, so it's just returning either true or false, depending whether the game is over or not. So if the game is finished, then it's true, and otherwise it's false. And then we also have a utility function or objective function. So this is actually give you like a numeric value, a final numeric value that ends in terminal state S for player P. So as I mentioned, like in adversarial search, we assume we have two players, right? So we have min and max. And so you always consider that max makes the first move. So that's our main player. And then min is just trying to block max or minimize his chance of winning. And so, for example, in chess, one player tries to checkmate the other players, right? And then the other one is trying to just avoid it. So here's just how to represent the game with initial state, which could be, for example, board configuration of chess. We have a successor function, which are list of moves and state pairs. We have a terminal state identifying whether the game is over or not, and then a utility function, which is just giving you a numeric value. For example, if you are playing Tic Tac, then we have, for example, win, showing it with +1. Which means that max wins. So we always see the game from the eyes of max, okay, which is our first player. And so, for example, this shows a state where max wins. This shows that max loses or O wins, right, or min wins, sorry. And then draw, which is actually, we could have some states that none of them can win, right? And so I'm really getting worried. What is happening here? So the root of the tree is the initial state. If I continue the same way, I think in like, it was about 3 minutes so far, so 3 people left. How many of you left in the class? So I think I have like about half an hour to explain everything so fast. So the root of the tree is the initial state, and the next level is all of max move. Why? Because max is your first player, so he makes the first move. And then min plays, so it's a turn-based game, right? So first max starts, then min, and then it goes forward the same way. And it just shows, for example, how many, for example, blank squares is left at each level. So in terms of the size of your search tree, let's say, so this is, for example, the game tree that you have in Tic Tac playing, right? So here you have some initial state. Always max player is starting the game, right? And then he can have like 9 different moves, right? Depending on where we put X here. And then let's say X is here, so max move is this one. Then depending on this, we have several moves for O, right? So for example, O can be here, here, and so on. And then it can continue the same way, right? And so we continue until we reach to a terminal state, which when the game is over. When the game is over, when can we say the game is over? Either max wins or lose, right? Or we, like all the blank states are taken. So for example, here is when the utility function is -1. And why is that? Why the utility function is -1 here? So it could be either +1, -1, or 0 in this game. -1, yeah?
Because X loses.
X loses, right? So -1 is when X loses. +1 is where X wins. And X wins if we have, so I assume that you all know this, but in case you don't know. So this is the place where, for example, if we want to see when X can win, either all the horizontal blank spaces are occupied by X, or for example, we have like this, so either horizontally or vertically, or even diagonally. So for example, here, if we have this, then we say X wins, right? So looking at these 3 states, this one clearly O wins, and then this one X wins because we have X in diagonal, and then here, no one, right? So that's 0. So the basic idea is choosing the move with the highest minimax value, and I'm going to explain what is minimax strategies in like a few seconds. Choose the moves that lead to a win, even though min is trying to block. So you always look from the eyes of the max, okay? And max makes the first move, tries to maximize his win, and then his opponent's move, turn, which is min's turn, to minimize that. And so max goal is to get to 1, that was the utility function 1, right? And then min's goal is to reach to -1. So if n is terminal, we use the utility value. It means that the game is over, we reach to the final state, and then we can return the utility value, right? If n is a max move, so if we have not reached to the last step yet, so it's either min's move or max move. So if it is max move, then take maximum of successors, because max wants to maximize his chance of winning, so it takes maximum of all possible states, right? And then if it is min's move, means always trying to minimize everything, so it gets the minimum of all the possible values in your successors. So here is just an example. Now, here it's showing that, for example, this is max move, and at this level we have min's move. So max moves are all shown with this, what was it called? Rectangle? Triangle, yeah. So it's with the triangle, and this one is also a triangle, but it's the opposite way down, right? So I call it reverse triangle. So we have triangle for the max and reverse triangle for the mean. So how does it work? So max always takes the maximum value of like these, right? Which are actually what was calculated before by mean. So you start from here, for instance, we have, this is like a depth first search, right? So you start with here, which is your initial state or max move, and then you go into this branch, and then you go deeper until you reach to the leaf node. So that is similar to what we had in depth first search. And now you reach here, you have 3, and then 3 is returned to this node, because so far 3 is the minimum, right? So min here is trying to get the minimum value. So the only value we have so far is from like A11 is only 3, so 3 is returned here. Now what does DFS do? It's going to the next one, right? So we backtrack, explore this one. Now this one returns 12. Now between 12 and 3, which one is minimum? 3. So should I change the value here? No, you don't change it. And the next one, should I change it? No, so it again returns 8, but the value is not updated because min is trying to minimize the utility for max, right? So this node here just returns 3. And then we backtrack again, right? So we backtrack and return 3 here. So now 3 is here, and we do DFS, so we are going to explore here, this branch now. Now, at this branch, so we first go like deep into the left one, A21. Now in A21, it returns 2, right? So the value here is now 2. And then again, according to DFS, we have to explore this one. But should I update the value or not? No, you don't, right? Because it's not the minimum. The same is here for 6, right? So 6 is returned, but the value is not updated. So the value that min is actually returning from like this tree is 2, which is the minimum. So from this branch, we return 2, right? Should I update the value here? No. Why? Because it's a max, right? And max only updates it if we return a like higher value. So far, 3 is the max. So now you go to the third branch, and then you continue the same way. So you go deep into this branch on the left, which is, A31. A31 returned 14, but we don't update this value, right? Actually, we have at first, we have 14 here, and then we have 5, but because 5 is less than 14, the value is updated to 5, right? And then it goes to 2 because 2 is even lower than 5, it updates it to 2, okay? So here we have 14, 5, and then finally the value is updated to 2, which is the minimum. Now 2 is returning here, but we don't accept it, like the max wants to get the maximum from all these 3 branches, which was 3 so far. So the value that is returned at the end is 3. And what would be the path then? So the path is what is actually led you to this result, which was this path, right? So this path was actually what gives us this result. So this is just the algorithm for a minimax. So you have this minimax decision function, which is returning an action. So you always, like in your successors, you have possible moves, right, from the state that you are starting. And then based on the moves or actions that you have, then the next player decide what to do. So now the next player, so we have like this minimax value here, which actually identifies what we return depending on whether, for example, the next state is terminal, or if it is max move, or it is min move. So if it is terminal, just returning the utility, right? So the utility value just showing, for example, the result. And then if the next state is not terminal, and if it is max move, then we want the highest minimax value, right? But if it is the min turn, then we want the minimum value. So the same way as what we did here. Here, for example, it was min's turn, so we returned the minimum value. Here it was the max turn, so we returned the max value. So in terms of completeness, optimality, and so on, is this complete? So did we do a complete search in the example that we had? Yeah, so far, if we consider 2 players are playing both like optimal, then yeah. And we are not considering any like alpha beta pruning. I'm not discussing this session for now. So it's just pure minimax algorithm. And as we have seen, we like explored all the states and all the nodes, so it's complete. And is it optimal? Again, at this stage, yes, it's optimal against an optimal opponent, right? Because we assume that both players are playing their optimal moves. And then in terms of time complexity, assuming that your maximum tree depth is m, so you can go deep onto the m depth, and b is the number of legal moves or, for example, the branches that you can have at each point, then the time complexity would be b to the power of m, right? So for instance, in the previous example, let's say we go up to depth 3, right? So which depth did we go? Like we go to up to depth 3, and then we have also the number of possible moves that we have is also 3. Then at the end, we have like nine branches, right? And in terms of space complexity, it's just BM, right? Because we have depth first exploration similar to the DFS that we had before. So now let's see this one. So here, what is the first move? The first is a max player, right? And in most like AI problems that you'll see, X is considered max, O is min, okay? So most of the game. So here, always your first player is your max. So here first player is X move, so this is our max, and we are trying to play from the eyes of max. So we wanna like try to maximize his win. Now, how many states can we have here at the first level? For max 9, right? So we can take like 9 different moves. And then how about O? 8. So because 1 is already occupied by X, so now O has like 8 moves. And then as we go down, it like reduces. So can you tell me how many are the total number of moves here? That is how many nodes we can have. So we have 9. And then 8, right? And then 7, and then 6. 9 factorial, right? So that's 9 factorial, the number of the nodes that we can have. And so as you can see, at each level, one of the players, so this is a turn-based game. So at each level, one of the players are playing. So this is, for example, X move, and then this is O move, right? So for example, if X is here, then move can have, for example, this move or this move or this move, depending on where you put O in like those left blank spaces, right? The blank spaces that left. And then let's say, for example, from like this branch, if X is here and then O made this move, what are possibilities here for X? So X could be here, 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 right? So we have like these 7 moves, and then we continue the same way. And then so as we've seen, we can have 9 factorial moves because we have like 9 here, and then each of them can have like 8, and then each of them can have 7 moves, and so on. And so now we want to see how we can calculate the evaluation function for example, this example. Let's say we start from here. So this is our current board, which was O's move. And then so this will be the X move, right? So because O made this move. Now, what are the X possibilities? X have 1, 2, 3, 4 possibilities, right? X could be here, 5 possibilities. Here, 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 and so on. So depending on where you put X, which is shown here with a bold X, so you can have like these different 5 states. Now, how did we calculate this f of n, or utility evaluation function? So evaluation function measures the goodness of board configuration. So how do we do that? So you consider the number of possible wins for your max, which is X here, and you minus actually the number of possible wins for the opponent. So what does that mean? For example, for here, if you want to calculate the f of n, so you see how many possible wins we have that are not blocked by the O for X. How many possibilities do we have that X wins here? So one possibility is this one. So we have all X in the first row. How about the second row? Do we have any possibility for X winning here? No, that's blocked. How about the third row? Blocked. So far 1. Now go to the columns. So in the first column, does X have possibility of winning here? Yes, if we have all X here, so X can win. So there is 1 possibility here. Second column, yes. Third, blocked. So far, how many? 3. And now let's look at the diagonals. So this one is already occupied, so blocked by O, and so it remains only this one. So we have 4 here. So this will gives us the number of possible wins that are not blocked by the opponent, or number of possible wins for max, which is x here, right? Minus, now that you have calculated the total possible wins for max, you also have to calculate, because we have another opponent, right? We also have to calculate the number of possible wins for min and then reduce it from the possible wins for max. Now, what are the number of possible wins for min here? Your min here is O, right? Now, let's see how many possibilities of winning we have for O. Now, for this row is blocked by X, right? So O cannot win here. Here, second row cannot win, right? Third row can win, right? So we can have like all O here and O can win. Now look at the columns. How many possibilities in like these 3 columns we have for O winning the game? 1 possibility, right? So 1, 1, 2 so far. And in terms of diagonal, because we have X here and also X blocked here, so there is no chance for O winning diagonally, right? So the total number of wins for O here is 2, and therefore your f of n, or like your evaluation function, returns 2 for this state. And then you have to calculate the same thing for like all these states, right? And then you propagate the results to the previous levels. How do you propagate the results? Let's say, for example, you have 2 here, 3 here, 2, 3, 3. What number should I return to the previous state? Depending whether it was the mean move or max move, right? So we had the max move here, right? And max tries to maximize. So among these, you have to return the highest number, which is 3. So is this clear? Okay. And so in Minimax search, you expand the game tree by m player. So we go to the fixed depth, because sometimes your like depth can be like go a long way, so you try to put a limit similar to what we had in DFS, right? We use DLS, depth limited search, to limit the search. And then applying evaluation function at the lowest level, what we did here, right? And then propagate results back up the tree. So the key idea here is that instead of searching the whole tree, which is too large, we can go to a limited depth and then evaluate positions there. So here, can you calculate f of n here at this level? Let's say these are our leaves and we want to calculate f of n. Do we have any volunteer? Even if just for 1 node, yeah. So 4 possibilities for X to win. How many possibilities do we have for O to win? We have more. We have first column, third column. Yeah, so the evaluation function for this one will return 1, right? And the same way you calculate for all of these nodes. And then what do you have to return? Let's say this is 1, this is 2, 1, 3, 4, 1. So you have numbers from 1 to 4. Which one do you return to the previous state? Minimum. Why? Because this was the O move, right? Which is the mean move. And so we return the minimum. So depending on which state you are returning to, if it was a max move, you return the maximum. If it was mean move, you return the minimum. So here, we propagate minimum value of children to the parent, which was this one. And then, so if you see, we're just doing it for like leaf nodes, and then which are the children of only this node. But then again, we have to like do it for all of them, right? So, and then this propagate the maximum, because this is the max move, right? So at the max move level, we return the maximum to the parent. And then again, we propagate minimum, because this is the mean move. And here again, we propagate max, right? So here again, we propagate max. And so here is another exercise for you. So who can? Do we have any volunteer for this one? You just basically, this is very easy. So we have like max, which is shown with these circles, and then we have mean, which is shown by triangle, right? And then you have to go like depth first search, and then explore all nodes, and then returning either minimum or maximum at each level depending on which player's turn is, right? So any volunteers from here? Yep.
I guess since you already have all the values, you would return maximum to the previous layer. So then it would look like 5, 7, 9, 8, 6, 9. Then you would take the minimum of those. I think the minimum of those was 5. And then you would take the maximum.
Yeah, so you take the maximum at this level because we have max here, right? So you go depth first search here, and then you return 5. So if you want to go algorithmically, like based on the algorithm, you just say, okay, you return 5, right? So this node will be 5 first, and then you go check this one. If it was more, you update this. If it was less, you don't update because this is maximum, right? So this will remain 5. And then you return 5 value again here, right? And then you want to like explore this branch. Now in DFS, you go again deep here. Now you return 4 here, and then you have 7 here. So you have to update the value of 4 and return 7, right? And then so you have 5 here, 7 here, right? And then this is the mean. So you have 5 here, 7 here, so it returns 5 here. Now we have 5 here, and we have also 5 here at first, but then we have to also check this branch. So we go deep here. This will be 9 first, and then we return 3 from this branch, but it doesn't update this value because this is max, so it will remain 9. The same here, this remains 8, this remains 6, this remains 9. So from this branch, out of 9 and 8, it returns the minimum, which is 8. We had 5 here, 8 here, right? And then the here we have like 6 and 9, which returns 6, right? Which is the minimum. And then we have 6, 8, and 5, right? And then we return the maximum, which is 8. So that is how you calculate the value at the root node.